start with one of, I think, sort of one of the biggest topics in Calc 2, in that it's a somewhat completely new idea. It's the first sort of major brain stretching application of integration, aside from just saying what is an integral itself. At least in the first one in a mathematical sense. So we're going to use integration to find the volume of certain objects. Okay. So one of the earliest questions investigated, I guess, in the history of mathematics, it actually helped lead to the creation of calculus, and it was what was the volume of a given object. Now we're going to approach volume in the same spirit that we sort of asked, what is area and how can we solve that? Okay. Now, of course, we know that to find area, you just did an integral. Now, to do volume, we're going to use integration, but we have to think about how we're going to use integration. So here we go. So let's start with this. For what basic object do we know the volume?
Sphere.
Okay. So a sphere. Okay. So two things. So first of all, how do you know the volume of a sphere? Is that something that's obvious? No. Is it a formula you memorized? Yes. Okay. So since you brought that up, one of the things we're actually going to do is prove the formula for the volume of a sphere. Okay. So that being said, what is the basic object for which we know the volume? Okay. Cube, or slightly more generally, a rectangular prism or rectangular block. And its volume is length times width times height. Okay. So naturally, we want to be able to figure out the volume of more complicated objects. What about a barrel? What about a pyramid? Things like this. Okay. So to talk about how we're going to extend our idea, let's go back to talking about two-dimensional area. So remember, the basic idea behind two-dimensional area was we said, well, area in general is height times width, but we use calculus to solve this problem. When the height is changing, say it's f of x, first we approximate the area by saying it's the sum of f of x times delta x. Then we approximate it using rectangles. And then we say, well, it's exactly the integral from a to b f of x dx. So that was it. That was a 5-second summary of a lot of weeks of work. Okay. So now let's extend that to 3 dimensions and 3-dimensional volume. Okay. So volume is length times width times height. Now, in order to make this nice and general, I'm going to simply say this is the same as area times the width. So does everyone believe that? Okay, so we don't often see volume formulas in this form, but if you think about it for 1 second, this is pretty straightforward that this is true, because the length times the height is just the area of one side, and then times the height. Okay. So once we know this, we can say the exact same thing we just said. What if the area is changing? Right? So with a rectangular solid, you always have the same area. It's always a rectangle with the same dimensions. But what if it's not? For example, a barrel. A barrel, what's the area on the face? You all know what a barrel roughly looks like? Okay. It's a circle. But is it always the same circle? No. Barrels get wider in the middle. Okay. So if that area is changing, we can say, all right, let's approximate this by saying it's the area at x times delta x and take the sum of all that. And then if you want the exact volume, what do? Integral. You take the integral. So the exact amount is that. Okay. So that was a nice bit of logic, but we have to really understand this if we're going to use this in practice. So let's take a moment to see how a single slice with a width of delta x is a solid with a volume A of x times delta x. Okay. So what are we looking at right now? Right now, we're looking at some kind of shape, and what we're saying is we have some kind of shape, and we know what the area is. Now, the way that I've set this up, so when we talk about area, what do we mean? We're going to talk about cross-section. So, for example, if you have a cylinder and you take a slice through the middle, you get a circle, and you always get the same circle. If you have a rectangular prism, a rectangular solid, take a slice through the middle, you get a rectangle, and you always get the same rectangle. But now we're going to look at the case where it's not the same. So in this case, what we have, if you take every slice, you get a square. However, you don't always get the same square. And we can see that by taking a look right here. So I don't want to talk about the formulas right now. I just want to talk about understanding what's going on. So what's going on? At every x value, there is a slice. Now, what is the width of that slice? We just call that delta x. So that's the idea. So we think of it as being like some kind of thin slice. Now, what's the area of that slice? Well, the area of the slice in this case is determined by the fact that the slices are squares, or that the face, the cross-section is a square. So in other words, all we need to know is at each x value, what is the length of the side, and then we'll know the area is that squared. So at every x value, we can say the area is something squared, and then the width is delta x. Now what happens, and that's the volume of each single slice. So for example, if you look at the little thing over here, here's the slice when x equals 0.3. Here's the slice when x equals 0.7, et cetera, et cetera, et cetera. So we could think of every x value. At every x value, there's this thin slice. And this thin slice has a volume, the area times delta x. Now, what do we do if we want to approximate the volume of the entire thing? We add all those little volumes up. But now we know mathematically what to do once that happens. We know that the approximation is just the sum of all those little volumes. But we know if we want to make this approximation exact, we take the sum, delta x, and we just turn it into the integral dx. And now it's exact. So we have an approximation of the volume, which we turn into the volume exactly. Okay. So does this make at least a tiny bit of sense? Okay. It'll make more sense as we go, but I just want to check in. All right. So one of the things that we're going to want to do is to be able to visualize these things. So let's also continue to visualize this, and this is the solid that you get. So this is kind of a on its side slanty pyramid kind of thing. Not exactly, but something like that. So the easiest of these problems is the one where we know first of all, we know what the formula for the area is. We know A of x. If you're given A of x, piece of cake. So the first thing we're really going to do is one step slightly harder than that, which is where you have to do maybe one step to figure out what that formula is. Okay, and there's the link for what I was just showing you. Okay, so right now we're actually going to figure out what is the volume of a pyramid with a square base. So in order to make this easier for us to do in terms of calculations, imagine that the pyramid, instead of pointing up, is pointing to the side. So the base is at x equals 0 and the tip is at x equals 2. So it's pointing along the x-axis. So a cross section at each x value is a square, and the side of the square is 2 minus x. Now just to help us visualize this, when x equals 0, what is the length of one side going to be? It's going to be 2. And when x equals 2, what's the length of the side going to be? 0. So in other words, it's the point of the pyramid. Does that make sense? Okay.
Sorry, can you repeat that again?
So just to help us visualize, to understand this is really a pyramid, on its side, when x equals 0, the cross-section is going to be a square, and the side is going to be 2 minus x, so the side is 2. When you get out to x equals 2, it's going to be a quote-unquote square, but what's the length of the side? 2 minus 2 is 0. So it's really gotten all the way down to a square that's just a point. And obviously, in between, you're going to have squares that are getting smaller and smaller.
So basically, we know that it's going to be from 0 to 2, because at 2 it's already 0.
Exactly. So right, so now we want to ask ourselves, what's the volume? So, what's the volume?
So wouldn't that be x minus
Volume is the integral
0 to 2?
from 0 to 2. I'm just going to start out by just putting a of x dx. And you can always start like that. Now the question is, what's the area?
X minus 2 times x minus 2.
Well, just to be more consistent, what's the length? What's the length of a side? 2 minus x. And what's the area of the square going to be? 2 minus x squared. Because that's just the area of a square. You take the side and square it.
Not u equals 2 minus x.
Could do that, or we could just multiply it out. I think multiplying it out will be easier. Okay. So this is the integral from 0 to 2. So multiply this out, you get 4 minus 4x plus x squared dx. This will be 4x minus 2. 4x squared over 2, so 2x squared plus x cubed over 3, and that's from 0 to 2. So this will be 2 minus 2 squared plus 2 cubed over 3 minus 0 minus 2 squared plus 0 cubed over 3. Oops. Okay. And if we work all that out, we get 8 thirds. Okay. So, and I just want to point something out here. We're solving for volume, so I should have made units here. Let's see. So let's say length measured in meters. So if we're measuring length in meters and we're finding the volume, then what's the units of the volume? Right. So you could either write it as cubic meters, but I'm not going to do that. I'm a mathematician, so I'm going to write it as meters cubed. Okay. So this is sort of like the next level of complexity, because as I said before, an integral by itself we think of telling us the area under a function. However, we can use integration to find other things. So what we just are seeing for the first time now is that you can use integration to find a volume if you set it up correctly. Okay. Sorry? Okay, so next, let's do this one. There we go. So, what is the volume of a barrel? Okay, so we got a barrel. The barrel's 4 meters long, and the cross section at each x value is a circle with the radius determined by that formula.
Can we take an integral with pi arcs?
Yeah. So
That's
first-
exactly right.
So first,
So
every-
the first thing I want to do, not that you have to do this, but I'm a visual person, I like to do it, is I like to draw a picture first. So what does this look like? Well, this looks like the cross section at each x value. Let's see, so it's 4 meters long. So I should have specified it's going from 0 to 4 if that wasn't obvious. Let me see. So I'll say 0x4. Just to be clear. Okay. So what this looks like, so here's 0 and here's 4. So what's happening here? So you've got this and this. And then if you were to work it out, what you would see, do this a little better, is that it looks something like this. So when I say it's a barrel, I literally mean it's the barrel that we all know and love. If you were to graph it, you get something like that. Okay. And again, at each x value, so for example, let's take x equals 2. So when x equals 2, what is the radius of this thing?
0.
No, check it.
Divide by 4.
Yeah, you plug in 2, the part of it is 0, but 4 minus 0, so you get 4. So for example, when x equals 2, that was a great circle. All right. All right, that's the best I can do today. All right. You get a circle and radius equals 4. Obviously, at a different x value, you're going to have a circle of a different radius. So, for example, when it starts, when x equals 0, what's the radius?
0.3 minus
4, let's see, at 0, so you get 4 minus 0.3 times 4, so 4 minus 1.2. So over here, radius equals 2.8. So anyway, so in other words, I didn't lie. In the sense that you've got a barrel, it circles, where the circle is smaller on the end and bigger in the middle. That's all I wanted to convince you of. Of course, I already told you about that when I said it's a barrel. All right. So we now want to know what's the volume of this thing. So anyways, that's the picture, that's the idea. So if we want to find the volume, how do we set that up?
Integral from 0 to 4.
Right. So in general, it's just going to be a of x dx. But now the question is, what's the area? Yeah, the shape is a circle. The area of a circle pi r squared. Great. Okay, but now we gotta change that again, because what else do we know?
R.
We know r. And r was what? That thing.
Chain rule, right?
So no chain. No. What's the easiest way to do this problem?
So
Just substitute 0. It's multiplied out.
Multiply it out.
Yeah.
So now we're just doing. At this point, we're doing algebra. X minus 2 squared is x squared minus 4x plus 4. So this is now 4 minus 0.3x squared, then plus 1.2x, and then minus 1.2 squared. Let's simplify that. So this is negative 0.3 x squared plus 1.2x plus 2.8. Got to square that. Oh, dx. Okay. So I'm going to try to do this in my head as quickly as possible. You get 0.09 x to the 4th minus 0.72 x cubed. All right, this is hard to do in my head. 1 second. Okay, so sorry about the numbers working out so weird, but it works out like this. And now integrating this, again, the decimals are messy, but as far as the calculus, this is very easy to do because it's just a polynomial. Okay. So sorry, in the interest of time, I'll just say the rest of this is pretty easy to do. And the other thing I want to say is think of the pi as a constant in front. You just leave the pi hanging there. So you'll wind up with pi times something. Okay. All right. So any questions about this first idea of how to find the volume? Okay. So the short version is, once you know what the area is, or the area function is, you need the integral of the area dx, and that gives you the volume. Okay. Okay. Now we're going to look at a variation on this. So knowing the area, so again, we call the area the cross-section. So what if you know the cross-section, but we're looking at a slightly different scenario? Let's revisit that first pyramid problem. What if we switch the variable to writing everything in terms of x to writing everything in terms of y? Then it would be this statement. The base is at y equals 0, and the top is at y equals 2. A cross-section at each y value is a square, and the side of the square is 2 minus y. So now how do you find the volume?
You just do dy.
Yeah. You do it, just like I said, everything instead of writing x, you write y. So the volume would be the integral from 0 to 2 a of y dy. That's just going to be integral from 0 to 2. So the area, since it's a square, it's the side of the square squared dy 0 to 2, 4 minus 4y plus y squared dy. Anyway, blah, blah, blah. We already did this problem. The only thing is we've erased x and written y in its place. And this worked out to be 8/3. Okay. So the fact that I've replaced x's with y's, we can interpret this in two different ways. Number one, you can write this in any way you like. You could say, let's say the base is at r equals 0 and the top is at r equals 2. We can just write everything using the variable r or z or whatever you like. And we know that just changing a letter from one thing to another doesn't change the problem. We do everything the exact same way. So one way to interpret this is just say you can use whatever letter you want. It doesn't matter. But there's another interesting way, which is to imagine what this graph really means. Now when you represent this visually, the pyramid is pointed up along the y-axis. If you really want y to mean what we usually have it mean. And we're thinking of area as a function of y, a of y. And in addition, we did the integral dy. So when we take little slices, where's the width? The width is being measured not along the x-axis, but along the y-axis. So instead of slices, let me see, these slices were squares. So instead of slices before, which were squares like this, we now have where, actually, let me be a little more. There we go. So where dx gave you a slice that looked like that, where the width was going along the x-axis, what do we now have? We now have a little dy that goes vertically along the y-axis. And slices are squares like that. Okay. So this now lets us do problems with objects oriented in a different fashion. So let's do this. Find the volume when the region is bounded by x equals 4 minus y squared in the first quadrant, and a cross-section at each y value is an isosceles right triangle. And just to be clear, the right angle sits on the y-axis. So one way to do this problem is to say, oh, I can't deal with x-axis, y-axis. Let me just rewrite everything in terms of y as a function of x. So you could do that. That would actually be a reasonable way to solve the problem. But let's try to work with it the way that it is.
So first we need to find the boundary.
Yes. So I'm just going to set this up in general. So it's going to be the integral from a to b. And the way we've set up this problem, I set a cross-section at each y value. So the way that it's written, our variable is going to be y. So it's going to be area as a function of y dy. Okay. Now the question is, at each y value, what's the area? Well, to help see this, let's draw a picture. So what does the graph of x equals 4 minus y squared look like? Well, it's a kind of parabola, but where does the parabola go? Yeah. So it's now x as a function of y. So a regular parabola like this would instead look like this. However, notice that it's a minus y squared. So you'd have an upside down parabola with y as a function of x. So now it's just going to look like that with x as a function of y. So the only thing we have to figure out is where exactly that parabola sits.
On x4. And then it's going to be equal to the 4.
And it sits right there. So one way to see this is that when y is 0, x is 4. Yes, okay. Wrong way around. And when y is, let me see, when x is 0, y could be either 2 or negative 2. Okay. So you can solve this algebraically really quickly. So if we just take for granted for a second that this is the graph of this formula, now what does it mean that each cross-section is an isosceles right triangle? Well, let's take, for example, the slice right here. Okay, so what does it mean to have an isosceles right triangle? Well, what is an isosceles right triangle? It's that. So I gave a tip, which was the right angle sits on the y-axis. So the right angle should be sitting right there. So we got to build an isosceles right triangle there. So it's going to look like that, if you will. Wait, that's a little... Actually, let me draw it this way. So like this and this. And imagine that you're looking at it from the side, so that's a right angle. Or from imagine you're looking at it askew, because we're trying to represent three-dimensional things on two-dimensional paper, and that's always hard, right? So long story short is that at every y value, you're going to have some kind of right triangle. And again, imagine that these things each have a thickness of delta x, if that helps. And naturally, as you get closer to the ends, you're going to have smaller triangles. Okay. So, the volume, okay, so what is the area of that thing?
The area of the triangle.
It's the area, and what's the area of a triangle?
Well, what is it?
Area is half times the base times the height. Okay. Now, what's the base in this situation?
Our formula.
Yeah, the base is the formula.
What would be the height?
What's the height? Well, what's the shape? It's an isosceles right triangle, so what's the height? It's the same. Because what do we know about an isosceles right triangle? The base and the height, same thing.
Oh, okay.
That's why I made it an isosceles right triangle. Okay. So this side is the same as this side. Okay. So the base, now I'm going to write this symbolically. The base is actually the x value. And then the height is going to be the same, so again it's going to be x. Okay. And so we know we're going to integrate half x squared dy. But what do we know that x is? What is x?
4 minus y squared.
X is 4 minus y squared. I'm going to square it, dy. Okay. And now what are the limits of integration here? Where does the shape start and where does it stop?
-2.
So it's negative 2
So it's gonna be.
From -2
So then
to 2.
should we do this whole thing as a absolute value since it's from negative to positive?
Don't need to worry about that.
2 steps from -2 to 0 and then
Yeah, actually, you should simply do it the way that it's set up, and you'll see it works out as you'll see. Okay. You don't need to worry about absolute value because we've written down everything correctly. That always is the area always is half times 4 minus y squared squared. That's always the area.
Even if you do the absolute value, you're gonna end up with the same value, right?
Yeah, and notice that what's built in is 4 minus y squared is always going to have a positive value. It's always this length.
Because the y is never influenced here by the delta y. The y, the base is never influenced by the delta y. So if delta y is negative, the base is still going to be positive in this case.
We don't think of, I mean, delta y is the width of each slice. And then what's the area? The area is always this formula. And then notice that even for negative y values,
So
it's
it's
going to
gonna
give
be
you a
positive.
positive value. So you don't need to tinker with it. It's fine the way it is. Okay. Okay. So from here on out, it's just, how do we do this integral?
Channel.
Yeah, multiply it all out.
Multiply it out.
You can do it channel.
No.
Just do it with integrate with x instead of
You mean at this step?
yeah.
Can we integrate this and get x cubed over 3?
No, because it's our variable is y.
The variable is y. So the reason I wrote down x in that step, so this is important, so let's take a moment for this. The reason I wrote down x in that step is because, as you can see, we're going to want to get used to using different letters to represent different quantities. But we also have to do that, as we do that, we have to keep in mind that our variable is our variable. And the way we've set this problem up is that the slices are little delta y's, so we're going to integrate dy, our variable is y. So when you integrate, you better be integrating with y as your variable. So, and notice that when going back to the picture, the base is actually just whatever the x value is. But x is a function of y. Okay. So, so this winds up being 8y. So, and I'm just actually here. I'll just say this: half 16y minus 8y cubed over 3 plus y to the 5th over 5, and that's all from -2 to 2. Now when you plug in 2, so let's see, we do all this out, we get half 32 minus 64 over 3 plus 32 over 5 minus, and you'll see something very interesting happens. You get -32, and you get minus 64 over 3 minus 32 over 5. But what interesting thing happens? That subtraction in front is going to make all of those into additions. So this is where the reason we didn't need the absolute value, well, we don't need the absolute value, and as you see, it works out properly, where you're just always adding stuff on. So this just winds up being whatever, arithmetic, whatever that works out to be. Okay. So, Right. So switch that. Okay. Just realized that. Yes. So I just realized that in the question I actually said in the first quadrant, and then I forgot to answer that question. Now, all is not lost. What can we do?
Divide by half.
Just divide by 2. Just from looking at the picture, it should be clear that this is actually half. Now, if I'd done this correctly from the beginning, what should I have done? I should have done the integral from 0 to 2. Because the first quadrant would simply mean this part. So it should go from 0 to 2. All right. So that being said, let me go back and fix that. Okay. So it's going to be 8.5 and 8 and 16, 8 and 8/15. Okay. So sorry about that. I just had to chop and erase the bottom half because I said in the first quadrant, but there it's fixed. Okay.
If we have an irregular shape object, how would we go about?
Okay. So yes, just so as a reminder, if you're not happy with the expression x equals 4 minus y squared, naturally you can just turn this into y equals 4 minus x squared because you're talking about the same object, but instead of sitting on the y-axis, it's sitting on the x-axis. So obviously when you do that, the volume doesn't change. So you're finding the same volume. Okay.
And the quadrant stuff can be changed.
It's still, the first quadrant is still the first quadrant when you do that. So instead of sitting on the y-axis in the first quadrant, it's sitting on the x-axis in the first quadrant. But yes, if you do that transformation, you have to make sure that you get things right. Okay. Now, that being said, we are going to encounter problems where you're going to have to be able to think of either dx or dy, and that'll be coming up either today or next time. All right. So what we've talked about so far is solids where I tell you or almost tell you the formula for the area. So we're going to look at one slightly interesting application of this, or a slightly specialized application of this, I should say, which is what happens when you get a solid not just from me telling you what the cross-section is, but in the following way. What if the solid is created by taking a region bounded by some function and revolving it around the x-axis?
We had this question, you form
What does that look like?
You form circles between
Yeah. What is the cross-section, and then what is the formula to find the volume?
to find the volume.
So what does that look like? Can you imagine it? Okay. So one helpful way to think of what the solid is going to look like is to think about what's going to generate volume. And one way to generate that volume is to take a thin delta x slice. So if you have your original graph and you have your region, a thin delta x slice is going to look like a rectangle, like from when we first learned what an integral was. So what happens when you take a thin rectangle with delta x and you revolve it around the x-axis. What do you get? To help figure that out, awesome. Hold on. So let's take a look. So here we've got this function, and we have some, and again, so we have a thing of having a starting point and a stopping point. And we're going to say, well, let's approximate that region, that area with rectangles. And we're going to use those rectangles to approximate what happens to that region when we spin it around the x-axis. So what do we get? So what do you get?
We get a cake.
Right. What you get is little cylinders. So, or another way to think of this is, what is the cross section? What's the area? It's a circle. So every cross section is a circle, and the area, of course, is pi r squared. And what's r going to be? What is r determined by?
The x, the length,
The length of
the x-axis.
The length of this thing. And what is the length of this thing in this problem? It's y, and y is f of x. Does that make sense? So again, so the key thing, so two key things. When you form a solid by making a revolution, always it'll be the case that what you get is a cross section that is a circle. That should be clear from this illustration. That's the first thing. The second thing is you have to figure out, so we know we're going to integrate area, in this case dx, and we know the area is going to be pi r squared. You have to figure out what that radius is. So in this case, the radius is very simple. It's the function. So let's take a look. Okay. So let's do this problem. So this is, in some sense, this is a special case of all the work we just did, where the area isn't something in general. For a solid of revolution, the area is the cross section is always a circle. So we're always going to use pi r squared in some way. Okay. So for this problem, find the volume when the region bounded by y equals x squared, x equals 1, x equals 3, y equals 0 is revolved around the x-axis. So again, just to understand it, let's take a look. So what does this look like roughly? Well, we all know what the function x squared looks like. Got this parabola. And then it also says it's cut off at x equals 1. So that's that. X equals 3. That's that. And then also y equals 0. Y equals 0 is the x-axis. So what we want is that, so that's the region that we're talking about. And we revolve it around the x-axis. Okay. So the volume equals the integral. Well, I should ask you. So it's going to be the area, and we're using, are we using delta x or delta y? Or dx or dy? We're using dx because the little slices are oriented in that fashion. Little widths along the x-axis, in that direction anyway. So everything's going to be a function of x, so it's going to be a of x dx. And what is the formula for the area? Pi r, it's going to be pi r squared. And what is r in this case? It's the function which is just x squared. And we should be integrating from where to where? From 1 to 3. So this is the integral pi x to the 4th. This is going to be pi x to the 5th over 5 from 1 to 3. And that will just be pi, let's see, we plug in 3 and we get 243 over 5 minus pi 1 over 5. So 242 over 5 pi. And that's 48.4 pi. Okay. So this is sort of this is a different sort of case of thinking about how do we find the volume of a solid when that solid is generated as a volume of as a solid of revolution. Cross sections are always circles. Okay. So this kind of new but kind of same application. Yeah.
So that's the one that's
I'm sorry? Yeah. Revolved around the x-axis? Well, here's the x-axis, and we are revolving it that way. It would be cone-ish, I guess. So actually, what would it be? We have the tool to take a look. So let's take this. So let's just say x squared. And we want to, what did we say? We said let's go from 1 to 3. Hold on. There we go. Okay. There you go. So that's what it looks like. All right. Now, technically, it's not a perfect cone because a perfect cone has straight sides. So it's kind of cone-ish. Make sense?
Like a loudspeaker.
Is that just an applet or a cover?
This is an applet.
Did you write that with applet?
Okay. Whoa. All right. So I think we're ready to have you guys try one. Find the volume when the region bounded by y equals the square root of x equals 0, x equals 4, is rotated around the x-axis. Okay. So let's talk about how to do this problem. So I always say, let's just draw a little sketch just to make sure we're doing the right thing. So the graph of square root x, y equals square root x, you should know it looks like this. And we're going from 0 to 4. And then rotated around the x-axis. So you wind up with something like that. Okay. So now, what's the volume? So we know it's going to be an integral. So it should be integral. Actually, I should ask you, what's the variable that we're going to use? We're going to use dx because our little slices, our little slices are little delta x's. So a of x dx. And so we know the x is going to go from 0 to 4. And the area is going to be pi r squared. And r is just whatever the y value is. And the y value is the square root x. So you're going to go from 0 to 4. pi x dx. So this is working out to be an easy one. Integral from, oops. So this is pi x squared over 2 from 0 to 4. And that's just 8 pi minus 0. It's just 8 pi. Okay. So we're going to look at one twist on this. What if we rotate this around a line that is not the x-axis? So I've drawn a nice little graph of this problem, which is find the volume when the region is bounded, when the region bounded by y equals x squared plus x plus 2, and y equals 1, and x equals, oh, I changed that, sorry. X equals 1 and x equals 2 is rotated around the line y equals 1. So now we really got to draw a picture to understand what's going on. So where's the region? The region said bounded by y equals 1. So the region is right there. Now what does a slice look like? A little slice looks like that. And where are we rotating it around? This line. Okay. So when we do that, what's the shape of a slice going to be? It's still going to be a circle. Okay? So we know that we're still, so volume is still going to be the integral of ax dx. And it's still going to be pi r squared. But the question is, what's the radius?
Radius should be that minus 1.
Yeah. Does that make sense? The radius is not just the value of the function. It's the distance from here to here, which means it's the value of the function minus the bottom thing, which is 1. So radius equals x squared plus x plus 2 minus 1. And of course we're integrating from 1 to 2. Okay. So that's one little trick to keep an eye out for. Does that make sense? Okay. Now, once you get used to it, you'll know, I'm bounded at y equals 1, and I'm rotating around y equals 1, so I have to subtract that distance. Until you get sort of used to just reading it straight out of the problem, I think you can see the usefulness of having a picture there to help you out. So it always helps just to draw a little sketch of what's going on.
And that would look the same on the apple.
One more idea, which is again is an extension of what we already know. It's just with one tiny twist. What if there is a hole in the middle created by a second function? You just subtract away that part. So what do I mean by that? Take the region enclosed by y equals x and y equals x squared and rotate it around the x-axis. What's the volume? So first of all, let's make a sketch so we understand what this means. So y equals x, of course, is just this diagonal line. Y equals x squared is just this parabola. So where's the region? It's this little slice, right? So we've already looked at talking about enclosed areas between two functions. So that's this idea. Now we rotate it around the x-axis. Now when you rotate this around the x-axis, what do you get? Yeah. You get a bigger circle and a smaller circle, and there's a hole in the middle. So how do you find the area of a circle with a smaller circle cut out? It's the area of the big circle minus the area of the smaller circle. And that's exactly how you find the volume also.
In the radius, can you just subtract both of them just so that the
Uh,
radius would be that?
No, you cannot. And I'll show you why. So how do you do this? So first you have to find, one thing you have to do is find your boundaries of integration. But a quick check, I think you'll see when x is 0, they're equal, and when x is 1, they're equal. So I'm just going to skip that step in the interest of time. So from 0 to 1, so we're going to take the one volume, so the outer volume minus the volume from the hole, which is the volume we're literally taking away. So what's the volume of the outside thing? Well, it's the integral of area dx. I labeled it area 1 to distinguish it from the other one, area 2. Now I'm going to squeeze this together as one integral. Usually we take integrals apart. I'm putting the integrals together to see that what we want to do is do the integral of pi r1 squared minus pi r2 squared. So the first one is the area with that radius, and the second one is the area with that radius. And naturally, the radius for the first one, for the top, the outer function is y equals x, so its radius is x. The inside function, which creates the hole you're taking away, is the function x squared, so that radius is x squared. So you wind up with the integral of pi x squared minus pi x squared squared. And the rest of this is just very easy to do. Obviously, it's the setup that's difficult in these problems. Okay. If you do it the other way around, what happens? Get the exact same thing but negative. Okay. And one comment, someone just asked me, can you just do the one radius minus the other radius and square that? Is that the same thing?
The radius is changing.
Yeah. Exactly. Also notice that r1 squared minus r2 squared is not the same as r1 minus r2 squared. That's just a fact from algebra. Okay.